Okay, so now we're going to look at the different factors that affect the solubility of a solute in a solution. So there are three main factors. There are more, but these are basically the three ones that are most important. The first one is the ion size, if there are ions involved. The second would be the interactions between the solute and the solvent. And the third is the temperature. All right, so let's look at the nature of the solute and solvent. And there's a general rule that is used for predicting whether or not a substance will dissolve in a solvent. And that general rule is like dissolves like. What that basically means is that polar substances will dissolve in polar solvents, nonpolar substances will dissolve in nonpolar solvents. Now, it's a general rule. There are some exceptions, of course, when rules are general. So what you'll find is that polar and ionic compounds, as I said before, tend to be more soluble in polar solvents than nonpolar solvents. So for example, if you take the compound sodium chloride, which is ionic, and try to dissolve it in water, in ethyl alcohol, and in benzene or ether, what you'll find is that sodium chloride is, of course, very soluble in water, water being very polar. It is slightly soluble in ethyl alcohol because ethyl alcohol is less polar than water. And then when it comes to the compounds ether and benzene, which are essentially nonpolar, what you'll find is that sodium chloride is simply not soluble in those solvents. All right. On the other hand, if you take, well, before we get to the other example, let's look at what happens at a microscopic level when you try to dissolve sodium chloride in water. So as you can see here on the screen, this is the sodium chloride, which of course exists as a crystal lattice consisting of sodium and chloride ions. And what happens is that the water molecule will approach either the sodium or chloride and form a strong association with the ion. And that strong association, the energy that is produced from that association, will be used to break the bond between the sodium or chloride, or sodium, between the sodium and chloride basically. And therefore it will pull away the ions. And as you can see here, excuse me, the water molecule will basically surround the ions, forming a sort of cage, and therefore stabilizing it and keeping it in solution. So that's basically what happens when an ionic compound like sodium chloride is dissolved in water, right? It forms an ion or ions that are said to be hydrated. In other words, the water molecules basically surround the ions and keep it in solution. Okay, so I was about to mention also, as I said before, in keeping with the like dissolves like idea, nonpolar compounds, they tend to be more soluble in nonpolar solvents. So for example, benzene, which is very nonpolar, very has no separation of charge whatsoever within the molecule. It's a hydrocarbon. It's very insoluble in water, which is, of course, is polar, but of course it's soluble in ether, which is nonpolar, right? So this is another demonstration of the like dissolves like rule. As I said before, there are some exceptions, but generally that's what you will observe. Okay, so let's look at the effect of temperature on the solubility of compounds. Now, what you'll find is that most solutes have limited solubility in a specific solvent at a fixed temperature. And what you're going to see here is that the effect that temperature has on the solubility of solutes is dependent on whether or not the solute is a solid dissolved in a liquid or a gas dissolved in a liquid. So what we're going to look at first is the effect of the temperature on the solubility of the solid in a liquid. And what you'll find, generally speaking, is that solids will increase in their solubility when the temperature increases, right? So when you increase the temperature of a liquid, you increase the solubility of the solid in that liquid. There are some solids that are where the increase is only slight with increasing temperature, and there are other solids where the increase in solubility is markedly dramatic when you increase the temperature. Now, there are very few compounds that are solids whose solubility decreases with increasing temperature. All right, but those are in the minority for the most part. All right. And as you're going to see in the next diagram, in the next graph, any point on the solubility curve represents what is known as a saturated solution of that solute. All right. So here is the graph. The y-axis gives you the solubility. The x-axis gives you the temperature, right? And as you can see, for most of these solids, like sodium nitrate or potassium nitrate, there is an increase in the solubility with temperature. And that is certainly true in the case of potassium nitrate. Look at this line right here. As you can see, there's a dramatic increase in the solubility with increasing temperature. All right. There are other substances like the aforementioned sodium chloride, whose solubility is only slight in terms of increase when the temperature is increased. All right. And then you have, as I said before, some exceptional compounds whose solubility in water decreases with increasing temperature. And lithium sulfate is an example of that. All right. So those are some solids. And as I said before, most of them increase in solubility when the temperature increases, but there are a few, like lithium sulfate, where the solubility decreases. And there are reasons for that, which I won't get into in this discussion. This is basically a table showing you the solubility of alkali metal halides in water. And you'll notice that if the metal is the same for these halides, then the solubility tend to increase going down the particular halogen or group 7 group. So fluorides are generally more soluble or less soluble compared to chlorides, compared to bromides, compared to iodides. And that is true for the lithium salts, true for the sodium salts, not true exactly for the potassium salts at 0 degrees. You'll notice here, for example, that potassium fluoride, its solubility is 92.3 here, and then for potassium chloride it drops to 27.6, and then for potassium bromide it increases to 53.5. So there's some anomalies there in terms of the solubility and the type of halide when it comes to potassium. But the trend is maintained at 100 degrees Celsius. So there are several factors, of course, involved. Too complex for us to get into for our purposes here in this discussion. Okay, so we talked about solubility of solids in water. What about the solubility of gas in water? And what you'll find is that the solubility of gas in water usually decreases with temperature. And to be perfectly honest, I can't think of any exception to this. There may be exceptions, but that's generally what we know. And we can explain this observation using the kinetic molecular theory. Basically, for a gas to dissolve, it must form bonds with the molecules of the liquid. So if you increase the temperature, you're imparting kinetic energy to the gaseous molecules, which will be sufficiently energetic to break the bond between the gas and the liquid, the water. All right. And there are two curves which demonstrate this in this diagram that we saw earlier. If you look at the one for hydrogen chloride at 1 atmosphere, you see clearly that there's a solubility decrease when the temperature increases. And the same is true, the same is true for sulfur dioxide, as you can see down here. All right. Okay. So that's basically the effect of temperature on the solubility. So let's look at the effect of pressure. And this, of course, applies to gases, the solubility of gases in water. What you'll find is that small pressure changes have little effect on the solubility of solids and liquids and of liquids and liquids. But of course, in the case of gases, that is not true. Small pressure changes for gases can have a dramatic effect on the solubility of liquids. And there's actually an equation, which I won't get into. You're going to learn about it in Chem 1, if you have to do Chem 1, where there's a relationship, a mathematical relationship between the solubility of a gas and the pressure of the gas above the liquid. There's a direct proportional relationship between the two. So basically what that means is if the pressure of the gas is doubled, which would automatically mean a doubling of the number of gas particles if the volume is constant, then the solubility of the gas will be doubled as well. So there's a linear relationship between those two variables, pressure and solubility. All right. As I said before, there's a law called Henry's law, which is basically what describes what's happening here, and it's a mathematical equation which I won't get into here. Okay, so we're going to stop here, and then the next thing we're going to discuss is saturated, unsaturated, and supersaturated solutions. Okay, until next time.